Now we are talk about the modulation bandwidth of a LED. Mainly modulation bandwidth, there are two types of modulation bandwidth. One will be optical bandwidth and another will be electrical bandwidth. Let's first discuss about the electrical bandwidth. In case of electrical bandwidth, suppose n is our n is our concentration of the carrier concentration at the active regions. Then the rate of change of a carrier concentrations, that is J divided by QD minus N by tau C. Here J divided by QD, it is the rate of generation of the carriers. Means if our LED is keep in forward bias, then our carrier increase, generation of the carriers increase, means the rate of generations of the carrier concentration also get increased. But n upon tau c is the rate of generation of electron hole pair. So when electron hole pair generate, then the carrier concentration actually get reduced. So the rate of change of carrier concentrations, dn by dt, that must be J upon qd minus n by tau c. J upon qd can also be written as I by q, and then n minus tau c. Here the J is the current density and the D is the depletion thickness. D is the depletion thickness. Here we use the tau c. Tau c is the carrier lifetimes, and it is the carrier lifetimes of radiative generations, also non-radiative generations. Actually tau c, here written tau c, the formula earlier we also have discussed. Tau c equal to 1 upon tau n and non-radiative generations lifetimes plus 1 by tau r, that is radiative generations lifetimes. This formula earlier also we have discussed. So this is the rate of change of carrier density. So now at the steady state, in case of steady states, means this is my current, this is the power of the LED. In case of steady state, means current is a constant, then the power is also will be constant. Then the carrier density is then the rate of generation of the carrier must be 0. Means the steady state means constant current means the carrier generation would be constant. Change of carrier concentration would be 0. Then this derivative terms is 0. From here we get the n is here, if you equate to the 0, then we get n is J by qd tau c or I by q tau c. This is the steady state carrier density. But now we change our current. So this is the modulation response. The modulation response is analyzed for the different frequencies. This is also called the harmonic response. We will analyze at the different frequency. Means sometimes we increase our light intensity and sometimes decrease our light intensity. So our current also get increased or decreased simultaneously. Then how the power gets changed, what is the then the another analysis also done. Let input current to the systems. Input current to the system I is IB plus IM sin J omega nt. Here IB is the biasing current, that is suppose the DC current. Here the entire term IM and this exponential means this is the sinusoidal terms is added to this biasing terms, so that we are in the stage of modulation response. Means our current is changing sinusoidally, and the omega m is the modulating response. When our current get changed, so our output response also get changed. So we will see how when my current is changed, then how this carrier density get affected. So our carrier density is now n is nb plus nm e raised to the j omega mt. Simultaneously, according our current, our carrier density is now returns nb some constant terms and nm, this is the sinusoidal term is added for the as we added in carrier, as we added in current. So in concentration also we added this sinusoidal terms. So now if we differentiate this with respect to the time, then dn this is the earlier equations. Dn by dt is I by q minus tau c. This is the earlier equations, and this is the current equations we assume, and this is the this, in accordance with the current equations, this is the concentrations equations. So this is our n. If we differentiate this n, this density terms n's, then if we differentiate this n's, now we get dn by dt. Dn by dt means dn by dt, we operate this d dt of n, means this term, this constant term get 0, means nm j omega m, nm j omega m into this exponential term j omega mt. So now we put this differential equation, that is this terms, to this equations dn by dt, and here this I terms, I is ib plus im e raised to the j omega t, we replace this equation I. So this I by q and im also by q e raised to the j omega mt. Similarly, this n equation is replaced to this n terms, so minus nb upon tau minus nm by tau e raised to the j omega mt. So this is our equations. So here, if we equate this omega terms 0, means we consider the dc apply, means the in case of steady state, then this term get vanished, this term get vanished, and this derivative term get 0. From there there will be ib by q and minus nb by tau c. Similarly, then we get, if we equate then we get the concentration terms nb equal to ib tau c by q, which earlier also we get this n terms in concentration term must be equal to j by qd tau c or I by q tau c. These terms also earlier we get. But now what I'm saying, this j terms, nm j omega m e raised to the power j omega mt, these terms, and then ib, this ib by q and nb by tau c, if we equate these terms at the steady state conditions, means this is our nb. If we put this value to this nb terms, then this and this negative signs so cancel each other, then we have im by q e raised to the power j omega mt minus nm by tau c e raised to the power j omega mt. Now take common exponential terms in both side, and here right hand side also im by q minus nm by tau c, and this exponential terms get common. So now cancel both side exponential terms. Now we have j omega m nm must be equal to im by q minus nm by tau c. Now this is the, but our objective is to find out what is the concentration term nm. So this minus nm by tau c taken to the right hand side and get common nm, so j omega m plus 1 over tau c must be im by q. So the nm is the im by q divided by j omega m plus tau c. This is the carrier density. Carrier density is im by q jm plus 1 over tau c. Again, see, if we put this on this frequency terms to 0, then we also get the steady state value. But this is the complex terms also we have. This is the carrier density at the modulation frequency. Now we compute the h of j omega. H of j omega, what is the h of j omega? Is the response of the carrier density. So h of j omega actually the transfer function. Suppose you have a system, so you have an input and output. Then we determine the h of j omega. This is the transfer function. So this is the transfer function, means this is the carrier density at omega frequency with respect to the carrier density at the 0 frequency. This is the ratio of h of omega is the output by input in case of control system. Similarly, here we can say also the h of j omega is n of carrier density at omega frequency with respect to carrier density at the 0 frequency. At the omega frequency, this is our carrier density, simply written im by q divided by j omega m plus 1 over tau c. At the 0 frequency, we have the carrier density is the this ib tau c by q. So if we put the ib tau c by q, here 1 over im, actually here im and ib is get similar. So I 1 by IMQ into tau c. This IM by Q term get cancelled, and if we multiply tau with this denominator, then we get 1 plus j omega m tau c. This is our h of j omega. This is our h of j omega is called transfer function. H of j omega is called also called response of a carrier density. Response of a carrier density. Here we have a complex terms. Here we have a complex terms, so we take the magnitude of h of j omega, which is 1 divided by square root of 1 plus omega m square plus tau square. This is our the response of the carrier density. So this graph looks like a low pass filter. So if we plot this h of j omega with respect to the omega this frequency, this graph looks like a low pass filter. Low pass filter. Now what is the frequency at which h of j omega value is half? So if we put with the half value, h of j omega is half, then square both side. 1 by 4 is equal to 1 divided by omega m square plus tau square, then omega m square plus tau square equal to 3, then omega m is the root 3 by tau. At the root 3 by tau c frequency, our h of j omega value is half. This is the omega m the frequency. Also 1 by 2 term is 3 dB frequency bandwidth. Here we get full wave half magnitude frequency. This is the root 3 upon tau c, and the FM frequency is root 3 by 2 by tau c. This is also full wave half magnitude frequency, root 3 by tau c. So actually our bandwidth depends only upon the tau c carrier lifetime. The bandwidth only depends on the carrier lifetime. This is all about optical bandwidth.